Thank you. Thank you everyone for coming. So about a year ago, a little bit more than a year ago, I had this wonderful experience of going to South Pole and doing this seismic experiment. It was very rewarding both in terms of the research and the personal experience. So I want to take this opportunity to talk about some of the initial findings, and more work will be coming soon. So in this work here, I want to first acknowledge the student, the postdocs, and the collaborators working on this. Also NSF and the Moore Foundation for supporting the work. EarthScope also provided a lot of the field support for this project. So Antarctic seismology has been there for a long time. There has been a lot of great work in this domain. And there are many, many different targets. You can be studying their crust and mantle structure. So you can look at their response, to glacier, ice sheet changes. You could be looking at seismicity in the region. You could be looking at some shallow structures in the ice or at the bottom of the ice. But no matter what, you will need seismic stations. So the figure to the left are showing you where are the seismic stations deployed in the past. You can see a lot of kind of like yellow triangles. Those are actually all temporary stations, so it might look pretty good, but it's actually all temporary. This area is actually as big as the United States, so even with the temporary ones, it doesn't look very dense. And the permanent ones are only the ones showing at the green square, so they are really sparse. So in the middle of the continent, only the South Pole Station has a continuous recording of seismic readings. And even the temporary ones are really difficult to deploy, right? The figures to the right are showing you when they, it's a complicated operation to deploy a seismic station there. And to retrieve it, sometimes it's even harder. You have to dig through really deep snow to get them. And running them continuously is a major challenge. At the same time, you might also notice that within the continent, it's actually very hard to have earthquakes as a source for the imaging as well. So that's another major challenge we will have to deal with. The development of seismic nodes really helped a lot in the last decade or two, but still it runs on battery, so continuous recording is still difficult. So in the last couple of years, myself and my team have been working very extensively on fiber sensing technology. And this technology transfers telecommunication cables underground into a dense array of seismic sensors. I want to use this as one example to demonstrate it. This is in Los Angeles, and this is a cable running from north of the LA Basin all the way to the Long Beach port. And over this 40-kilometer long cable, we're turning that into almost about 4,000 to 5,000 sensors. Here, the figure to the left is showing you like a real-time screen image that you can see on the DAS machine. This is about 20 something 30 minutes of data, and whenever it's showing blue, that's where it's relatively quiet, not much shaking. Whenever it's yellow or red, there is a strong shaking. So actually, each one of those little tilted lines is actually one car driving along the road here. And this big tilted line here, band here, is actually the train traveling along the same path. So it's a much stronger and a much longer signal. And you also can see this very horizontal line here, energy here, which is actually an earthquake. So relatively horizontal line in this figure shows that it travel across a large area in a very short amount of time, and a seismic wave is capable of doing that. And this technology works by shining lasers through the fiber and less into the echoes due to intrinsic fiber defects. And by shining, this laser frequently, you can measure the changes of the backscattering. If the fiber is shaking and the length might change slightly, and you will see a difference in the backscatter light. And because the fiber defect is everywhere, they are everywhere along the fiber, it really can turn every few meters of the cable into a sensor. For the for the goal of Antarctica seismology, DAS has the distinct advantage that as long as you can power the DAS unit, then this is a continuous running seismic array. So it's a very dense network. It also can be continuously operating. And the fiber can really be engineered to survive longer in such harsh environment. So since we had all those success in California and other places, we decided that maybe we should try to demonstrate it for Antarctica because of all those challenges in deploying sensors in Antarctica. So we want to do a demonstration. So that's what this South Pole DAS experiment really is. We got to know that there is actually a telecommunication fiber at the South Pole Station. So at the Amundsen Scott Station, there's a lot of facility there. There's power plant and everything, 100 people living there every summer. But one of the seismic station, actually that was the South Pole Seismic Station, the QSPA station. Because we need to be away from the noise from people, it was deployed about 8 kilometers away. And then they need to power it and get the data back. So they actually had a fiber deployed to connect them 8 kilometers long. So we want to use this as an opportunity to reach 3 goals. To first, just simply evaluate DAS on ice. Does it work in this environment? How well it works? And also we want to do some seismic imaging, either the Fern structure or the ice structure or the glacier base structure. And finally, we want to leave there long enough to detect some Antarctica seismicity because we know that the seismicity level is very low there. But in the past, you only have one seismic station. We might have missed things. So we want to leave there for longer to demonstrate that. At the same time, this is really a pilot. So what we are learning is really trying to get the long-term goal that DAS can be applied more broadly across Antarctica, maybe by deploying our own cables. This proposal was funded in late 2019 or early 2020. And that's, of course, when the pandemic hits, and then the whole project got delayed by 3 years. During that 3 years of waiting, there were actually several other DAS experiments on ice happening, and they're all very successful. Some of them happening in Alpine Glacier, some happening in Iceland, Greenland. There was also one in Antarctica. So despite all these successes, we still think there is a great value to do the South Pole experiment, partially because South Pole is unique that this cable was already in place. Most of the other cases, you have to deploy your own cable. And the cable coupling may not be excellent. So in this particular case, the cable was deployed when the suppressor station was deployed. And it was now buried. It was, a lot of people put a lot of labor into this. Second for that, to make this experiment possible. But also because of all the snow added every year on the cable, now the cable is buried probably on the order of 10 meters deep. The cable was not in any kind of conduit, just direct contact with the Fern. So the coupling probably is going to be the best we can expect. And also the South Pole Station actually have a power plant that powers the station, so we can deploy the sensor in a comfortable environment and let it run continuously throughout the year. Because of the lack of natural seismicity around this area, we also brought active source. So this is going to be active source plus passive experiment. During the 10 days, 2 weeks when we were there, we actually collected a lot of active source data. We brought that data with us. So most of the result you can see today is from the active source part of it. We only recently got the passive data back, and we're still in the process of analyzing them. We brought all, 3 different kind of sources. We bring the hammer, right? So based on, say, experience in California, a hammer strike, or after some stacking, you can see them on the order of tens of meters away, maybe up to 100 meters away from the short point. We also brought the PEG, a propelled energy generator. It's basically a 40 kilogram electric hammer. And this one, so generally you can see on the order of hundreds of meters away. We also brought a seismic Betsy gun, so you dig a hole and try to shoot it. Usually you can see this a little bit further, maybe up to kilometers. We did an experiment just on campus. You can see all the dust get shoot up from the hole we digged, and you have to use some weight to hold it down. Otherwise, the basicon will fly away. So we brought all of this, and finally, after 3 years of waiting, we got to do this. It was a long way to get there. Fly to Auckland, Christchurch, and then you fly to McMurdo Station on the edge of Antarctica, and then you fly to the Amundsen Scott South Pole Station where we are going to do the experiment. This is the airplane we took, and this is the inside of it. So it's really like people sitting with their cargoes. The experience makes you appreciate a little bit more of the commercial flight. You have cushions and air conditioning, very comfortable compared to this. But it was a very exciting trip. There was a lot of quarantines and testing at home, and then New Zealand, McMurdo, and finally at the South Pole Station. There was many times it seems that the entire trip will be stopped for whatever reason, all kind of logistic or COVID reasons. But eventually, we're very lucky that we went through everything smoothly. The quarantine at McMurdo Station was actually reasonably pleasant because we're not required to stay inside their dome. We were actually, as long as we are not interacting with the McMurdo staff, we are able to go outside. So this is a photo of the McMurdo Station with the Scott, the Discovery Heart, where Robert Scott started some of their trips in Antarctica. Was an interesting visit. And we were also able to take some beautiful pictures and some hikes near Mount Erebus. So after that quarantine, we were able to take this airplane to the South Pole Station. Was a beautiful flight, 3-hour flight. This is when it's actually flying over the Beardmore Glacier, which again is one of the major pathways from the McMurdo Station or the Discovery Hut when Scott was taking it to the South Pole. Actually, you can see the very shiny ice here, which is blue ice with very little snow on top. This is where they were actually man-pull all their equipment all the way from the ice shelves to the top of the plateau. So it was a very interesting experience. Once you get to the South Pole, this is other kind of facility you live in. It's actually a pretty big facility in the summertime. They can host 140 people, I believe. In the winter overtime, there are still 40 people there to keep everything running. Once we got there after the kind of quarantine, we're able to start working. Not only we deployed that, we also actually deployed some nodal seismic stations sensors as a calibration with support actually from our Earth scope. When you work outside, it is indeed pretty cold there. And, after a while, this is what it looks like in the field. But fortunately, a big part of the work was already done, right? Like the cable was already deployed. So we only had to, stay in this computer room within the South Pole Station and just connect this set of DAS equipment to the fiber. And suddenly we have 8,000 sensors. So on top of here, you can see the RU, which is the laser equipment. In the PU is mostly computer and a lot of hard drives. So in total, for the 1 year collection, we actually have more than 200 terabytes of data. For that active source part of it, we have a little bit over 10 terabytes of data that we brought back with us. We actually finished the setup of this DAS unit on one of the Sunday evenings, about 10 p.m. So it's very late. So once we get everything to work, this is what actually the screen looks like. So compare with the one you just saw in for Los Angeles, this is really very different. So essentially the entire thing is blue, right? That's of course because South Pole is a very quiet environment, very low noise. And actually later we did some more quantitative comparison. This is the noise power spectral density. The yellow line here is the South Pole Station, and the other lines, colored lines, are actually the ones from California. So you can see really it's a substantially quieter than any of our previous data arrays. When we see that, we were very excited. We want to test it right away, even though it's a Sunday evening. So the only source accessible to me at that time was this hammer. So I basically went out there with Martin sitting at the data machine, and I just go out there, find a place I believe was close to the cable, and then hammered the ground for about 40 times. That's as most as I can do in that elevation. I actually got pretty hot, even though inside because that parka is really, really warm. And then we go back, we actually can see the data right away. You can see it on individual strikes. And after some stacking of the data, you actually can see this wave propagating all the way to more than 3 kilometers from the short point. So this was very surprising, very pleasantly surprising, because in California, general hammer strikes, after you stack, you see them on the order of 100 meters. And now here, we can see them 3 kilometers away. We believe that that's mostly because the first, a very quiet environment, but also the ice there is very cold, and that leads to very low attenuation. So waves can propagate much further. That was exciting. So we decided the next morning we should bring up the big hammer. But this is what we saw when we went to the peg. We installed it the day before, and then at the morning we found that it's all frozen up. We actually spent quite a lot of time trying to unfreeze it with torch guns and so on. And then we go to the field, we have another problem. The snow in South Pole is actually very fluffy. So even after just 20, 30 strikes of the plate is starting to disappear in the snow and is outside the safety range of peg operation. So we had to do only on the order of at most 40 strikes at every location. But after all those logistical challenges, we eventually figure everything out. This is what it looks like in the field. So we drive this piston bully. So we stop every 100 meters along the road. And one person would come out, move the metal plate in position under the hammer. And you can see there's actually a black cable next to it is actually connected to a GPS unit that will give you location and timing of each of the strikes. That helps with their stacking of the shots later. So after about 30, sometimes 40 strikes, the plate is too deep to keep striking, and then we move on to the next striking point, 100-meter away. We were at this time waiting for their Betsy gun because they consider as explosives. So even when we have arrived at the South Pole, they were still at Los Angeles. So we basically are left with the peg only at that time. But then the data was actually on the first day was actually terrible. So we come back and we check the data, and it was worse than what we see on the hammer strikes. How could that be? Well, they assume we got to check the noise level, on the station, and we found that on the first day, on a Sunday evening, it was very quiet. No one is doing any work, so the human noise was very low. But this time when we were doing a Sunday morning, right, in 6 o'clock, people eat their breakfast. It was very low noise, but then quickly the noise increased by more than 20 dB. Okay, actually more about 30 dB of noise increase. And all those heavy trucks and machines working, making the noise very strong. And they take the lunch break, and then afternoon work, and then dinner time. And the breakfast and dinner time are the longest window we can have. It turns out because it's always, daytime there, in the night, there are people taking night shifts, and it is still pretty noisy. So to get good data, we're left with no choice but to go when everyone else is eating their breakfast or eating their dinner. So that means we have to get up really early, pack some cold food to the piston bully, go out to do the experiment, eat our, breakfast in the field, wait, or come back to sleep, and then do it again in the evening time. Of course, it's always daylight, so at least that part is not a problem. We're not working in the dark. But eating cold food in the piston buoy is not pleasant. Maybe the only pleasant part is to eat some ice cream that is cold outside. So as long as you put this ice cream in the back of the piston buoy, it just stays frozen very nicely. So we're pretty happy about that. Well, this effort pays off. We actually can see much further of the peg shots after stacking, some shots. So this is the particular profile when we were striking about a 1.2, 1.5 kilometer away from the South Pole Station. You can see their surface waves propagating all the way to 8 kilometers away, which is like the far end of the cable. You can actually see a little bit of the body waves, but they are not particularly good beyond like 4 or 5 kilometers away from the source. With this kind of data, because you actually have a 2D, right? Like you have a equal spacing in the distance direction, you have equal spacing in time. So it's regular in both. So all we do is just actually a 2D Fourier transform to change that into wave number and the frequency domain, and then change that to phase velocity and the frequency domain. And this is what the data looks like, right? So most of the energy was in between 0 and 100 hertz, actually a few hertz to 100 hertz. And this is phase speed. And you can see there are actually many, many modes we can observe. So there are actually 16 modes. The ones we start with R are the Rayleigh wave modes. The ones that started with P was actually the pseudo P wave mode. So this pseudo P wave mode, like the surface one, was actually trapped wave in the Fern layer because the Fern velocity increased pretty rapidly in the top tens of meters or 100 meters. With this data, we can constrain the velocity of the Fern layer really, really well. We actually take a slightly different approach because there was nearby there was a borehole, and people made a very accurate density measurement. In some other areas, people actually have derived scaling relations between density and seismic velocity using the formulation here. And some of these parameters, like A and K are the two free parameters, was actually calibrated in the past in West Antarctica and Alpine glaciers. So first step we took was say, okay, we have a density. Let's take these parameters people calibrated before and see, do they fit our data? And if we do that, we actually have the red line here as the measurement. So these are the peaks you see in the previous slide, the modes. And then the black background is showing the prediction. So you can see that with all these, calibrations from other places, it actually, captures some of the features, but really do not match the observations quantitatively. So that means this calibration is actually a fairly local thing. So what we do is then we actually calibrate our own A and K parameter. So after some Bayesian inversion, we were able to achieve a much better match to all the modes we are observing here. So with this new scaling relation that's unique to the Eastern Antarctica, which of course has the majority of the ice for Antarctica, I think this is probably a better scaling relation that we can use in the future when you don't have ice core density measurement to convert your seismic measurement into ice density. And this has some implications for estimating ice loss. So one of the methods of estimating ice loss was actually to use altimetry data to convert that into ice mass, but you have to assume a certain density. So here we show that if you use the wrong scaling relations calibrated in other place, you actually will cause a 3 to 7% bias in density. And it's probably better to use East Antarctica specific calibration here. So this is what we achieved by using the peg shots. And the other big target we have in mind was the glacier base. In particular, we want to infer what's the condition at the base in terms of temperature. Because if the ice is frozen to the bed or is on a thawed bed, that could indicate a very different profiles of ice flow. If it's frozen, it has to be done by internal deformation of the ice. But if you have a thawed bed, the ice could slide on top of it. And this have very different implications of ice dynamics. And this is actually not an easy thing to measure because you're under 3 kilometers of ice here. And what we want to get is a reflected signal at the base, from the base of ice. Right. And we hope, because this is now 3 kilometers away, we were planning to do this with the Basigan shots. South Pole is not the most exciting place in terms of constraining the basal temperature, but still there were actually debates about it. So some of the early papers using ice cube borehole temperature measurement extrapolated to the base suggest that the base was actually -9 Celsius, which is substantially colder than the pressure melting temperature. So that would suggest the glacier base is in a frozen condition. But a more recent paper in 2022 using similar data but added some other geophysical surveys showed that the temperature at the base is probably more likely to be very close or exactly at the pressure melting temperature. That would suggest that there, at the glacier base, there's probably like, relatively wet sediment, and that would, facilitate the glacier ice sheet sliding. So we want to be able to help answer this question as a demonstration what we can do broadly. So, the shipping of their Basigan shells took a long time, but about 3 days before when we have to leave, finally the shells arrived. So we did this test right away. So we go out there, we use battery to hold it down. We fired the Betsy gun. It was not even as impressive as we saw in California, where the dust is shooting up. We were concerned that the battery is not enough to hold it down. We actually don't need to hold it at all. So we were actually confused why that's happening. And then we go back to check the data. The data was absolutely terrible. Okay, so a single basic gunshot cannot be seen even as far as a single hammer strikes. And we're very confused why until we found that if you look down the hole we fired the Betsy gun, you actually see a little cavity there. So basically the snow is so fluffy and dry, and the explosion actually caused a cavity and used all the energy for that. And we would have to drill much deeper for it to be more efficient. But given the thickness of the fluffy snow in South Pole, we would have to dig many meters deep. So that's become kind of impractical. At that point, we are left with no choice but use our peg. But we know that the peg essentially sinks into the snow after 40 strikes, and we have to stack a lot more to reach the energy level of a basic shots as we expected to go to much longer distance and see the body waves better. So we use the brutal force approach. We choose a location, we strike it as much as we can, and we manually backfill the hole, and then put back the plate and strike again. And we did that for 1,000 strikes. So basically the entire morning we were just waiting and backfill the hole and then strike again and keep doing that for 2-3 hours when people are having their breakfast or dinner. It was pretty exhausting, but we got the data we need. This time with 1,000 stacking, you can see, this way much more strongly. The surface is much more clear, and you can see some of the pseudoacoustic P waves in their Fern layer to 8 km too. So we're going to look for the reflections in this data. Before we actually went to Antarctica, we actually did some synthetic simulations to see where their body wave should be coming in, showing as the dashed line, and you can see them some of the waveform simulations. But when we look at the raw data on the left here, even after stacking 1,000 times, you really do not see them. So we were very confused. So it's definitely weaker than we expected from the synthetic simulations. And then because we have a 2D like this dense array, we were able to do FK filtering. Once you do the filtering, this phase really comes out. It's still noisy, but it's definitely there. It turns out this travel time match what we expect from P2S reflection from the base, and we do not see the P2P reflection, which is a little bit another little surprise as well. It turns out we eventually figure out why. The reason is when we were doing the simulations, we assume very high Q throughout the ice column. It turns out if the glacier base is close to melting temperature, then at the base, the Q will be substantially lower in the last kind of 500 meters. If you consider that, the body wave reflected from the base will get substantially more attenuated compared to the surface wave. And that explains the weaker amplitude. Also, we found that the reason we do not observe the PP reflection is because if you have, we actually observe only PS throughout from about 3 kilometers all the way to the end. If you have a liquefied sediment, actually the reflection coefficients are fairly comparable at a certain distance and even bigger for PP at closer distance. And that would be inconsistent with the observation. But if you have a relatively wet sediment, which is what we expect if the glacier base is close to pressure melting temperature, is the PP actually would have a much lower amplitude than the PS wave. While this wave might still be observable if you have a much stronger source, like bigger explosives or a vertical geophone, it's not too weak for the DAS to observe them. But we can still observe the P2S converted phase. So at this single location, we actually think our data suggests the South Pole ice bed is thawed. This figure now shows the updated synthetic simulation with the right sediment and also attenuation. Now you do not see very strong, clear PP phase, but you still can see the PS phase. And the difference from the expectation was coming from attenuation and the reflection coefficients. And this is also more consistent with the new result that their South Pole glacier base is at pressure melting point, and the South Pole Lake, which was a major target for that paper, is have a long existence time. So that's what we learned from their active seismic data. Then we left the site and we left their instrument there running for the entire year. We only recently got the data back, so we're still in the middle of processing them. But we already get some really interesting results. I'm just going to quickly talk about them. The first one is seismicity. So some of the previous papers, when they have temporal arrays, did identify interesting tectonic event in Antarctica. So in our 1 year data at the QSPA broadband station, you do see events like this, but without other temporal stations, it's hard to locate them or identify, exactly what type of events they are. We recently checked one of those events on that. Actually, you can see pretty clearly the S wave energy, even in fairly raw data in this case, propagating across the array. If you zoom in, you actually can already see some kind of wave field phenomena in this case. So we are hopeful that we can, locate or get more information about these earthquakes using this DAS array. We also detected some kind of unexpected events. These are so-called Fern quakes. So they're not exactly like the ice sliding or crevassing event, but event happening within the top tens of meters of the snow. As the snow was compacting, sometimes they were, compacting in discrete event and actually produce shaking. So they produce this particular ones are very fairly close to the cable, where we're able to actually see very strong wave from that to the level we actually can image the rupture propagation of the Fernquake. It turns out this particular Fernquake was actually triggered by us using the hammers. So when we hammer in the place too many times, the Fern actually collapses and then it propagates out. By analyzing the data in more detail using back projection, we actually can see an area about a kilometer in length actually collapse due to our hammering. We are currently looking into the mechanics of the Fern quakes, but also looking for natural occurrence of this kind of Fern quakes. The long duration of the measurement also allow us to look at potential time-dependent structures. So this is our first result using NB noise correlations throughout the year and look at how the Fern layer structure is changing over time. So this is the surface wave, so I'm sampling mostly within the Fern layer. And the blue line here is showing the seismic velocity change. So you can see there's a very obvious change throughout the year, and it correlates really nicely with the temperature measurement shown in pink here. We're still trying to figure out the mechanics of this, but looks like the temperature change from a minus 10, 20 Celsius degree to in the winter time down to minus 80 degrees is substantial enough actually change the wave speed within the Fern layer. So that's very exciting. We believe this kind of resolution we have on the Fern layer and the temperature change could be really useful in some other regions like Greenland, where people are excited about Fern aquifers. So this might provide some new constraints of that problem. So here's my summary slide. I would really claim that South Pole data really works. It's a very high quality data due to the cable coupling, very quiet place, and the very cold ice that leads to fairly low attenuation. The active source experiment sampled via the Fern layer. We also got reflections from the glacier base. If I'm gonna do it again, I'll probably bring even stronger source so that we can see the reflection more clearly. But we believe the reflection already tell us the glacier base is at a pressure melting point that have higher attenuation and lower P2P reflections. This 1 year data is being processed, but we've already seen some interesting seismicity and the DVRV. Hopefully that would also shed more light on the kind of tectonic activity level of the South Pole, of the Antarctic continent in general. I think the broader impact of this is that we really showed that the potential of DAS for many other glaciology areas and questions. We of course have to worry more about how to deploy our own cables, getting the instrument powered, and maybe bring better source. But I think if the data quality is really quite good, and that could be a very useful tool for future Antarctic seismology questions. With that, I want to thank their supporting agencies again. I also want to add advertisement for this photonic seismology conference. Zach Speaker and I are organizing this October. The registration or abstract submission is open. I encourage you to submit your abstract and discuss more about this exciting new area. Thank you very much.
Thank you, Zhongwen. Really fascinating findings there from Antarctica. I really appreciate you sharing them with us. We've had several questions come in. Maybe we can start with some of these. I would encourage our live audience as well, if you have questions for Zhongwen, to please go ahead and submit those using the Q&A box. This first question here from Surendra, I think this was in reference to one of your early plots. You were looking at the noise levels in Antarctica relative to other locations, and they were asking why the Antarctic noise levels didn't match the dotted low noise model.
Right. Very good question, because we believe the South Pole is so quiet that at high frequency, it's already dominated by instrumental noise in this case. Okay, so that instrument is intrinsically be noisier than conventional sensors. So I think the South Pole is the first time I actually believe we actually see the true noise of the DAS instrument itself, right?
Okay.
At actually longer period, the South Pole Station is not particularly required. The oceans around Antarctica and other atmospherical processes actually produce reasonably, noise levels.
Okay. A question here from Emily asking about how you converted the DAS output, which is in strain, into ground motion to produce your power spectral density curves for comparison.
Yeah, that's still the same figure here. Thank you for asking. The way we do it is we believe a majority of the waves we are observing here are surface waves. And we know their phase velocity very well through the ambient noise correlation and the active source. So we convert them from spring rate to acceleration uh, using surface wave phase velocities as a function of period.
All right. Yingping had a few questions here, and I think one of them is maybe relevant to what you're just talking about. Given the noise levels, will the South Pole be a good place for teleseismic recording? And I guess as a follow-on, just wondering if you captured any teleseismic events in the DAS recording that you've pulled back thus far.
Yeah, we did. We actually have quite a few events that we are looking into at the moment. Um, so we are actually doing P-wave receive functions at the moment on this array. But of course, we have to borrow the vertical component from the QSPA station to do the deconvolution. But we are seeing some interesting result. So we can see that. But at longer period, you can see the noise of DAS is high. That's because, DAS always have this 1/f instrumental noise at long period due to laser drift. So we are not seeing much long period surface wave unless it's some of the strongest events.
We had a few questions come in here about some findings you showed, really interesting stuff at the end of your talk with regards to the changes in velocity that you were able to see in the Fern over time.
Right.
I guess one question, the temperature measurements, there's a question here, was if that was measured using DTS, which I guess is another type of fiber optic method. Were you
Right,
able
right.
to employ that to get any temperature measurements?
Right. South Pole actually have their own weather station. So they actually keep a very good track record of weather data. So this particular data we use is actually the surface temperature measured at South Pole. Their thermal property of Fern is well understood and calibrated. So we believe what we're going to do next is to actually using those models to predict the subsurface temperature. And we are not using DTS in this case.
So somewhat relatedly, do you have a sense for how deep that temperature dependent velocity change extends within the Fern, or is that would be part of the model that you're
That's
discussing?
that's that's what we are working at the moment. So we
Okay.
do have a pretty good frequency band that we can observe this and many different modes. So we believe we will be able to constrain that, but not
Nice.
yet. This figure
Nice.
is pretty fresh out
Yeah.
of data processing at the moment.
Uh, Michael Baker asks if you've tried plotting any of the changes in the Ferdinand velocity against air
Oh.
pressure.
That's a great question. We should try that. Actually, we were pretty confused about why some of the blue peaks are actually ahead of the temperature. So
Mhm.
maybe it's actually like other processes that correlated with temperature. Uh, they do have pressure measurement too, so we should try that. Thank you.
Zhigong writes in to say, great presentation. One quick question. Do you know the average duration and seismic moment of those Fern quakes?
Hopefully we will know that soon. So right now, okay, so we could just take the data we have and measure the amplitude using some normal scaling relation and calculate that. We kind of don't want to do that because we have to consider the special ice and Fern structure and attenuation structure in this case. So we hope we can soon do a true modeling, quantitative modeling of this, come up with a moment and getting the magnitude from that. Unfortunately, that hasn't been done yet. But I was standing right on top of it. I triggered some of them. There was a strong shaking, at least at zero distance.
Okay. Um, a few more questions have come in here. Some of these are using some abbreviations I might need your help with, Zhongwen. But
Yeah, the
Yingting's
cable,
asking,
right? Right.
existing fiber, is it SM or MM or both?
Yeah, these are single mode fibers.
Single modes, okay. Uh, Chris is asking on the same topic of temperature, did you take the LF-DAS data, DTGS, to compare to these records? It should track the surface data change as well without the absolute level.
Ah, excellent suggestion. We are in the middle of doing that as well. Yeah. Thank you, Chris.
Looks like we have a question here. What's the possible mechanism for the Fern quake? Is it something related to the process of Fern, turning into solid ice? I don't know if you have any.
Exactly. Yeah, that's exactly what's happening. So in general, we think of firm being the process of slowly compacting into ice. And you usually think of it as a continuous smooth process. And what these firm quakes are telling us, they are not always that. So maybe there is a layer of relatively weaker snow or maybe stronger snow. I don't know, like with a different crystal structure. And then once it's overcome its strength, and that layer will suddenly collapse. This process has been observed in the past, but not many paper has been on this topic in detail because it's just very hard to capture in very high resolution, especially in Antarctica environment. Many
Mhm.
people reported feeling them, but this time we were able to really constrain the rupture process of
Yeah.
this. You can see individual asperities on the rupture. We can constrain the rupture speed to be almost exactly 100 meters per second, plus minus 3 meters per second. And we're going to learn a lot about this. We believe the way it's propagating, like the collapsing of the layer is the mechanism. The propagation is probably related to how the fern or the snow layer is responding to it elastically as it goes out. But some kind of heterogeneity of the fern layer clearly need to be involved to explain why it look like individual asperities radiating seismic waves. A lot of
Yeah.
puzzles to answer.
And yeah, it's really fascinating result here. And be curious to see what you all discover. Maybe somewhat related, you mentioned that the depth of the fiber optic cable where you're measuring all this information, you think it's probably about, did you say
10
5 to
meter or
10
so.
meters buried? Do
Yeah.
you have
Yeah.
a, like, do you know how, to what accuracy do you know how deep it
We
is?
don't really know. The 10 meter comes from a very rough estimate based on how much snow you got every year and the compacting. There's no real measurement of that. The South Pole maintenance staff, they sometimes need to go check, and there is a hole that they can go down. It's on the order of 10 meters.
Okay.
Uh, so it's not very accurate, to be frank.
Okay. Fair enough. Uh, a question here from Dominic asking if you found any deep ice quakes.
Yeah, I believe we do. We haven't confirmed yet. We see some very um, spiky seismic events, very small and close by, with clear P and S arrivals, and sometimes you can see some multiples between like a converted phase between P and S. So that seems to be a classical signature of ice quakes. So we detected a bunch of them actually in that 1 year data. We haven't looked into their detail yet. It's a lot of data to crank through, so we are kind of in the detection stage and the classification stage. Hopefully, we will start to dive into each type of the event and get more details.
Looks like a question here from Srendra asking about noise levels on the DAS. So, do you know how much that might depend on sort of your gauge length and settings and whatnot, or even for that matter, the brand or vendor of interrogator that you're using?
Right. We don't have much information about the particular fiber. It's just 20 years ago, whatever telecommunication cable they have and they deployed it. So it's just a regular telecom. If we do have a specialty cable, I would imagine that would drop the noise level further. So that would be a good thing to consider for future experiment. I believe we have used the only real telecom cable on the entire continent. So in the future, we would have to deploy our own, and it would be nice to consider specialty fiber for that purpose.
Yeah. Zhigong writes in with a little self-advertisement noting that they've found some Fern quakes that have been remotely triggered by the 2010 Maui Chile earthquake. Just, we thought it was some ice fracturing, but they could also be due to collapse, as you mentioned, for the
Yeah,
Fern quake that
yeah,
you found in
yeah.
Antarctica.
Yeah. We initially when we felt it, that's how we thought it too. We thought we triggered some kind of made a crevasse or something like that. We actually went out there and looked for them on a snowmobile. And we didn't see anything. And there's a few other lines of evidence leading us to think this is a firmquake. I hope I have another opportunity to talk about that in more detail.
Okay, maybe our last question here, or one of our last questions. Yingping's wondering about solid earth tides, if any of that kind of thing observable in your data.
Yeah, so it's related to the question Chris Minto asked a little bit earlier. We are in the middle of doing that. So
Okay.
we do have a temperature calibration device, and we hope after removing that temperature effect, we can see some solid earth tides. The temperature calibration is for the room where the DAS unit is in. We believe along the cable, the temperature is either very stable or changing at a very predictable way, so we can remove them effectively. So that's one of our big target in this case.
Okay. A question here wondering about the cable. So it says the cables for telemetry and power supply for the South Pole station at Espresso. Does DAS require a dark fiber, or you can run this simultaneously while it's being
Right.
used?
Yeah, in this particular case, they do have more than one strand of fiber. So they have like a few extra fiber there for us to use. So this is a dark fiber case. I believe there are new instruments that do not require a dark fiber to work. But in this particular case, we are using dark fibers.